Morning, guys. Happy Monday. Today, I'm going to be finishing up 1.5. We just had a couple of little straggler topics left on that sheet. And then we'll be jumping into 1.6. We won't finish all of 1.6 today, but I'll give you an introductory kind of, flavor of what we're going to be talking about in 1.6. And then we'll call it a day, and we'll pick 1.6 back up tomorrow. A couple things of note. Last week, Friday, we did our very first lab video, and as a part of that, I had asked you to kind of turn your lab sheet in. Really, if you went through the video, it was essentially I went through all the questions, and I just wanted you to kind of work along with me, except for the last one. The last one I wanted your own unique individual answer. Okay, so if you haven't done that, I'm going to reopen that for you guys. I kind of had it closing last week Friday with the hope that people would be able to finish it on Friday. But if not, that's okay. I'll reopen it. You're more than welcome to finish that up. And again, if you haven't looked at it at all, it's about a half-hour video. And everything is walked through except for the very last part. You're responsible for answering that last question. Okay? All right, that's all I have. Topic two is due tonight. My bad. That is something else that needs to happen. So if you have not turned in topic 2 on It's Learning, please make sure you do so. If you have previously turned in topic 2 and you wish to change something or you needed something fixed or modified, please feel free to email me your most current version of that, and that'll work. It's not ideal. Ideally, it goes through It's Learning because it keeps my inbox nice and clean. But if need be, if you need to redo something or show me something different than what you originally turned in, please feel free to email me your new copy. All right, so let's finish 1.5, and we left off right here with the definition of ionization energy. Okay. This is going to play into today's lesson as well. So this tail end of 1.5 that we're going to talk about and 1.6 are very much connected, all right? So ionization energy. This is the energy required to remove the outermost electron, okay? The energy required to remove the outermost, oh my gosh. Hey, there we go. Great success. The energy required to remove the outermost electron, okay? So you've got an atom or an ion. It doesn't matter. It could be an ion too. You've got an atom or something with electrons around it. And ionization energy is describing, okay, if I put in a certain amount of energy, that amount of energy is going to be able to remove or get rid of the outermost electron, okay? This is a very important concept, and we're going to talk more about that in 1.6. All right, so ionization energy, the energy required to remove the outermost electron. How much does it take? With that, and with, again, kind of transitioning into 1.6, comes something known as Coulomb's law. All right, if you look at this definition or this equation on your sheet, it looks rather annoying. Good news, we will never use Coulomb's law mathematically, meaning I'm not going to require you to plug in any numbers for this. We're not going to do math. But conceptually, this is a really important concept. Coulomb's law is an overarching concept that shows up again and again and again and again in this class. All right? So this equation is it's there and it's absolutely correct, but in terms of the mathematical use of it, we will never plug numbers into this equation. And by the way, do you see that weird little like alpha kind of where the equal sign should be, right? It's not an equal sign, but it has this weird kind of alpha thing. That is proportional. Okay, that's the symbol for proportion. So the force, and again, Coulombic is in subscript there. So the force is proportional to Q1 times Q2 divided by R squared. Okay, so let me explain what this is. All right. Coulomb's law is used to describe attractive and repulsive forces between anything with a charge. So for us, obviously that's going to be atoms, other molecules, electrons, protons, things like that, okay? So we apply Coulomb's law conceptually to all of these charged particles. And we have these variables, okay? We have Q1 and Q2, which if you look over in the little box over here, Q1 is the charge of the first particle, Q2 is the charge of the second particle. So these can be positive charges, these can be negative charges, but Q represents the charge of the two things we're looking at, right? I'm looking at one electron and one proton. Q1 of this one is -1, Q2 of this one is +1, all right? R squared on the bottom is representing distance, okay? How close are these particles to one another? If I have a minus and a positive, or a minus, a negative and a positive, right? These are attracted to one another, okay? Opposite charges attract. Like charges repel. And Coulomb's law can be used for either. But if this is negative and this is positive, I know there's an attractive force between them. Let's say I bring them closer. Has that force or that attraction gone up, or has that gone down? Okay? I think you know the answer to this. It's gone up, right? If the distance between my particles is shorter or smaller, the attractive force should be stronger. It's kind of like magnets almost, right? You've got two strong magnets, and as you bring them closer together, it's like all of a sudden they're trying to, completely connect, right? So you can almost think of it like that when it comes to opposite charges. All right, so let's go back to ionization energy. When making predictions about which atoms will hold their electrons more tightly, Coulomb's law is what we're going to use, all right? So ionization energy, again, we're trying to remove the outer electron. How much energy does that take? Well, if we think about Coulomb's law, again, Coulomb's law is saying we have positive protons in the nucleus, we have a negative electron on the outside. How strong is that attraction, right? How strongly is that electron way on the outside attracted to the positive nucleus? If the answer is that it's pretty strong attraction, well, it's going to require a lot of energy to remove the outermost electron. But if the answer is that there's an attractive force, but it's not too strong, well, then it's just going to require a little bit of energy to remove the outermost electron. And again, when I say energy to remove the outermost electron, I'm actually talking about ionization energy. That's the term that we'll use. All right. So if the charge increases, in the middle here, I say if the values of Q increase in the equation, what happens to the force? Well, let me give you this scenario. I have -1. I have +1. There's an attractive force between them. I now have -2 and +2. Same distance, but bigger charges. Would we expect that to be stronger attractive force or a weaker attractive force? Okay. The answer is that it should be stronger. There's more positives, there's more negatives, there's more positives, and those forces of attraction are increasing. Okay? Now, that's Q, right? Bigger charges, stronger attraction. That makes sense. It's kind of intuitive. The distance. If we decrease the distance, right? If we bring these things closer together. I just talked about that on the last slide. What happens? The force also goes up. This is an intuitive concept. I think it's intuitive, right? It's not trying to trick you. It's not opposite of what your brain would naturally think. Bigger charges, stronger attraction. Charges closer together, stronger attraction. So we used Coulomb's law just qualitatively. And the word qualitative just means like in its general sense, right? Not actually using numbers. The opposite of qualitative is quantitative. Quantitative is when you are being very precise and using specific, accurate values and numbers and math. Okay? All right, so conclusion. The conclusion is this. Bigger charges, stronger force. Shorter distance, stronger force. And when I say force, this actually can be either attractive or repulsive. Again, if I have proton, and I bring them closer together, well, now they're going to be repelling even more strongly, right? Or if I have two protons versus one proton, again, the more positives, the stronger the repulsion. In general, we ignore the repulsion in AP Chem, okay? We are 99 times out of 100 talking about attractive force, all right? So when I say bigger charges equals stronger force, I'm really talking about, okay, negatives and positives, attraction, okay? And same thing, shorter distance equals stronger force. What I'm really talking about there is negative charge, positive charge, but they're closer together, stronger attraction, okay? All right, the last slide here is talking about what's known as the effective nuclear charge. We will talk about this in 1.8, 1.7. I forget which topic it is. It's coming up later this week. The effective nuclear charge is the charge that the valence electrons, valence of course means outer, the charge that they feel on the nucleus or from the nucleus of the atom that they're around. There's a generic qualitative equation that we can use. The symbol for effective nuclear charge is Z subscript EFF. Okay, that's the symbol for effective nuclear charge. And we can generically just kind of figure out a value of the effective nuclear charge by taking the total number of protons in that atom minus the total number of core electrons. So core electrons and valence electrons we talked about last week, right? Core electrons are all of the electrons in the inner or closer to the nucleus, right? The better way to find the core electrons is to understand which ones are valence. If an electron isn't valence, it's core. that's not, again, it's kind of a weird way of stating it, but if you can identify the valence electrons, and again, the valence electrons are going to be, for our purposes, they are the outermost electrons, and we can find them by looking at the highest energy level, s orbital, and p orbital electrons. Anything else in that atom is a core electron. Okay, so we'll come back to effective nuclear charge later this week in a different topic, but I just wanted to kind of throw it on this sheet because it's related. It's related to Coulomb's law. It's related to ionization energy. It's related to identifying valence electrons and core electrons. So it's a concept that kind of, is a part of what we're just finishing up here. Okay. All right, let me switch over to 1.6. We'll get a little bit into 1.6 and then we'll call it a day. All right, to start 1.6, I had a couple of questions on this presentation, and I'll give you a chance, right? If you want to pause it and answer these two questions, these are not on your sheet. If you want to flip to the back of a sheet or a margin somewhere and figure out where you could set this up, go for it. But pause it, try them, come on back. All right, first question, valence electrons, what are they? These are the outer electrons. More specifically, okay, the highest energy level S and P orbital electrons. Those work. Write out the electron configuration for iron 2+. Hint, valence electrons get removed first. This is a weird example, all right? Iron is element 26, and when we remove two of its electrons, all right, we're going to remove them from the valence shell first. So I'm going to start with my first electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, how many more do I need? Let's see, I got 10, 20, we need 6. That would be the electron configuration for iron if it was neutral, but it's not neutral, okay? I have iron 2+. The 2 positive charge means that I've lost 2 electrons. Now, when atoms lose their electrons, or they're taken away from them, they're losing valence electrons. So in our electron configuration, I have 4s2, 3d6. 3d6 is the last orbital that we put electrons in. So it seems or it feels like that should be the orbital that we take the first two away from. But in reality, when electrons are removed, they're always removed from the valence shell, or the valence electrons are removed first. So 4s2, that's the highest energy level 4. S is the orbitals we can remove from, so highest energy level S and P electrons are valence. In iron 2+, these have been removed. And the appropriate electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Okay? The 4s electrons are valence. Those are the ones that get removed. Let me fix one more thing. If you did the abbreviation, okay, which is absolutely just fine. This is argon. That is allowed as well. All right, I've transitioned over to a more personal environment here for the last part. So I'm going to go through a couple more things. Again, I won't get too far into 1.6, but let me just introduce it, and I'll pick it up tomorrow for you guys, okay? All right, so 1.6 is about photoelectron spectroscopy. Big giant words, which sound really scary, and you know, it's not as bad as you think it is, maybe. And I promise you, with this topic, kind of like I was promising you with when I started talking about quantum mechanics, right? And I was like, hey, there's 3D calculus, and there's, you know, all sorts of craziness with this. With photoelectron spectroscopy, what you're responsible for, or the questions that get asked about it, are actually pretty easy. I know as a teacher I probably shouldn't say that, but they're really not bad. So hang with me. I'm going to give you a little background. I'm going to explain what this is kind of about. But in terms of the questions you're asked at the very end of this, or you know, on a quiz or a test or whatever, it's not too bad. It really isn't. All right. So learning objective: explain the relationship between the photoelectron spectrum and, of an atom or ion, and A, the electron configuration of that, and B, the interactions between the electrons and the nucleus. All right. So let me get started. Photoelectron spectroscopy. This is an instrument, okay? We had already talked about mass spec, okay, earlier. That's topic 1.2. A mass spec is an instrument in chemistry that allows you to find the mass of different pieces or different atoms or different molecules, all right? So when we talked about mass spec, we were looking at isotopes pretty much is the way it was getting used. With photoelectron spectroscopy, also an instrument, okay, and it's called PES for short, which I'll show you later, and I'll use that pretty much exclusively moving forward. But PES hits your atom or your sample with an insane amount of energy, okay? And I say here that it's high energy electromagnetic radiation. X-rays, okay, X-rays and gamma rays, but gamma rays are very, very dangerous. So, but very high energy radiation is what we're hitting our atom or our chemical sample with, okay? And the idea there is that when your atom or sample gets hit with this high energy electromagnetic radiation, it completely removes all of the electrons. It's so much energy that we are just stripping the electrons off of this atom, okay? So, a couple of things of note regarding photoelectron spectroscopy. Again, PES, this is the abbreviation or the shorthand. The x-axis of the readout of the spectrum, or what the instrument gives you, is labeled as binding energy. And binding energy is just how strongly the electron is attracted to its nucleus. And the numbers on the x-axis are backwards. Okay? This is a dead giveaway that it's PES. The hard part, and you'll kind of see this later, and I'll be kind of mean with it later, is PES and mass spec, topic 1.2. Sometimes their graphs look really similar, really, really similar. But the dead giveaway, or the way that you know that it is PES, is the numbers on the x-axis are backwards. All right, and I'll show you an example of that in just a little bit. The y-axis is related to the number of electrons. So the further up a peak, or a bar, if it's a bar graph, means more electrons. So the height of those peaks are related to the total number of electrons in that area. Each peak on a PES spectrum is a different subshell of orbitals. So this instrument, okay, and the readout from this instrument is going to give us the orbitals. It's going to show all of these electrons existing in all of their individual orbitals. The further to the left on the spectrum a peak is, the closer to the nucleus that peak is, or that subshell is, all right? So, and I'll go over this again multiple times, but the x-axis on your graph, and on the next slide I'll show you, okay? The x-axis is the nucleus. The peak furthest to the, I'm sorry, I'm saying that wrong. The y-axis, I apologize. The y-axis is the nucleus, and the further, or the closer to the y-axis a peak is on one of these graphs, that represents an orbital closer to the nucleus, all right? All right, so here's the first question, and we will stop after this question, all right? Label each peak with the orbitals it represents. Which element could be represented by the complete PES spectrum above? Justify. So there's no peaks over here, I'll move my face right up there. But this is what a PES spectrum could potentially look like. Okay, here's the y-axis. Again, this is the relative number of electrons. I would like you to write right by this y-axis, you should write nucleus, or down here, nucleus, okay? This is more or less representing the nucleus. And as I travel left to right away from the nucleus, I'm going to hit my orbitals in order, all right? So this is the nucleus. I'm going left to right on my graph. I've hit a peak. This peak is the 1s orbital, the very first orbital of any atom, the one that's closest to the nucleus, okay? So this is the 1s peak. This is the 2s peak. This is the 2p peak. So this is a readout or a spectrum from an atom that has 3 orbitals, 1s, 2s, and 2p. But now the question is well, how many electrons are in each of those, right? So the height of the peak represents the total number of electrons. We know that a s orbital is a set of 1, and each orbital can only hold 2 electrons, right? So this height must represent 2. Now, it's a little annoying because the graph obviously is showing like 4 bars, but those bars are just kind of irrelevant. What we want to focus in on is this is relative. What is the relative height of this peak compared to the others? We know an s orbital can hold 2. This height must represent 2. So this is 1s, 2s, 2 electrons, 2 more electrons, and then we get to 2p. So if this height represents 2 electrons, what does this height represent? Okay, I hope you can figure that out. It's 3, right? It is a half taller than the other peaks, right? So this is 2, this must be 3. So in total we have 2, 4, 6 electrons. Good math. 2, 4, 7 electrons. Let's try that. We have 7 electrons total. Which element could be represented by the PES spectrum above? And that would be nitrogen. Nitrogen is element 7. It has 7 electrons. And we would expect to see this readout for that. Okay? All right, I'm all done. We'll pick this up tomorrow. I just wanted to give you a flavor of PES before we jump in with 2 feet. Please submit topic 2 if you have not. The lab stuff, I'm reopening up. If you have not finished the lab stuff, I would strongly encourage you do so. I will be giving you a grade on that as well. So again, please submit that to It's Learning, and I'll give you credit for that. Other than that, please email me if you need something, and we'll catch you guys tomorrow. Have a good day.